Hey guys, so in my last video I said occasionally I don't do things properly and feel free to tell me that I'm wrong. That was not an invitation to tell me that my version of physics is wrong. Okay, so I'm going to tell you how a torque wrench works, well, not the internal part, but the forces involved and why when people said I'm using an adapter and I'm going to put a torque wrench on it, I'm changing the torque on this nut. And that is wrong. And I will tell you why. And I will tell you why there is confusion about this change. Now, someone linked some videos of people trained to use torque wrenches trying to tell you that, yes, you should always keep it at 90 degrees and not do it like this. But I'm telling you that they're just saying best practices and they're not explaining what that difference is. Let's talk about what happens with a normal spanner. You know, maybe one of these, right? So we've got our spanner and we apply a force here. This is the nut, right? We apply a force here. Or maybe we use the ring spanner. You shouldn't really use these open-ended things, right? They're rubbish. So we apply a force here and we're rotating the nut, right? So what this is doing, we're applying a force, we end up with a torque. So if we apply 1 Newton, and this is 1 meter, we end up with a torque of 1 Newton meter, a Newton times a meter. So we've got this torque, and we've also got this, well, sorry, should be for every action, there's an equal opposite reaction, right? So no, we can just leave the arrow going this way. There's a force here, and there's that same force. So if the spanner had a nut that was free to float, we apply a force here and the whole spanner will just move down the table, right? Obviously it spins because there's friction here. In fact, it will spin about wherever it's touching the bench. So when there's no friction, if we apply a force here, the whole thing will just move down the bench. But it can't move down the bench because the nut is fixed to some global structure, right? So it's resisting this force. So we add a force, we end up with a resisting force and a torque applied. Okay, makes sense? If we extend the handle and we apply our torque out here, and this is 1, and this is 1, and this is 1. Now we've got 1 by 2. So now we've got a torque of 2 Newton meters. And we've still got this force coming down here of 1. This 1 is still a 1. Okay? This is the basics of torque. The other thing, that I should say is that we've got our nut. If we apply a torque here, so we apply this torque force on this beam, and this is 1, then this is 1. Doesn't change. If we apply it out here, it's still applied here as 1. This doesn't change at all. A torque anywhere on a beam induces a torque, anywhere, basically wherever it's rigid, that torque happens. So that is how this tool, this is a copy of my dodgy copy of the actual factory tool. So for people saying that I'm getting the wrong numbers, well, this is the factory tool from Yamaha. So you can forget that. But regardless, I'm saying it doesn't matter. It doesn't matter if this arm was much longer than the factory tool. So I'll show you why. So this is our rule. When a torque is applied, it's always applied at the nut. We can show you with spacegass. If you don't believe me, you can believe some software. Here you go. Check that out.
Okay, hello. Okay, so here we are in spacegass, which is just some engineering software for working out forces, usually in complicated structures, but today we're going to do something very simple, right? So we're going to have a beam of length 1 and turn on our reactions, and we're going to have this end being completely rigid and this end is going to be free. So this is going to represent our nut, and here's our spanner, and we're going to apply a load, a node load, case 1, and we're going to have a Y force of, say, -1, so that's down the page. We run the analysis so the computer can work out all of its physics. Geez, it didn't take long for that little model. And here's our reactions. Turn on annotation. And so we can see we apply our one, well, in this case it's a kilonewton, not a newton, 1 kilonewton. We get a reaction force of 1 kilonewton so that the whole thing doesn't just slide down the page. And we get a torque resisting that lever arm. 1 times 1 is 1 kilonewton meters. Now what we can also do, node load for case 2, is apply a moment of 1. So we're applying a moment of 1. We run our analysis. Look at our reaction. So we apply a moment of 1 and we get a reaction of 1. So even though the moment's applied out here, we get that reaction. Now, if we subdivide this into whatever, 3 equal parts, and we apply some loads, node loads, case 3, 4, and 5. So 3, we're going to do 1, 4, we're going to do 1, 5, we're going to do 1. 3, 4, 5. Okay, so now we're applying this torque at this point, which is only, how long has that been? 1/4 of a meter. Do our analysis. And then our reaction, so we apply 1 here, we end up with 1. If we move our force to here, the ½ meter mark, we apply 1, we still get a reaction of 1. So it doesn't matter where we put this force, we've always got a reaction of 1. Wherever you apply a torque, the reaction torque is the same. Okay, we've got those 2 components in our minds. So it's back to real life, Brendan.
Okay, now I'll just explain where the confusion comes in. So if I draw this again in 3D, something like this, right? We've got our arm. This is where the nut is. We're going to rotate this structure. We're going to torque this nut. Now, if we've got a torque driver in here and we have this is our torque driver up the top with our, whatever this is called, with our socket, driver adapter part, socketed in here. When we apply a force, we're going to apply this force up here, which induces a torque, which is torque happens down here and the torque happens in the nut. This torque wrench says we're applying a Newton meter. So we've got a Newton meter here, we've got a Newton meter here. This is how it works, and this is why I'm saying it doesn't matter how long this arm is because we're applying a torque onto this fixed plate, and this applies the torque. The confusion comes in because remember, wherever this force is, we end up with a resultant force up here. So we're putting a horizontal force and we end up with a force up here. Now what this does is our vertical driver, one of these, is being pushed over because there's a force at the top, right? So it's being pushed over. It's trying to bend. And what that's doing is applying an additional force here. So in my last video, you will see that when I was doing up the torque wrench, I was holding the head of the torque wrench, because when I'm applying this force, I don't want it all to roll over. I want it to rotate about this given point. So I'm holding the head so that this doesn't fall over. And if it's just falling over, it's applying a horizontal torque. So if you don't have a large extension, for example, you're just using the socket straight into this plate, you can see that leaning over part is incredibly short. It doesn't really happen. So your force out here is translated into an additional force. So the torque happens here, which transfers to our nut. That's fine, but we've applied an additional moment arm at this point. So we've actually we do increase the torque. But if there is an extension between them, then that force is way up here. It tries to make this fall over, which is, the longer this is, the easier it is to counteract. And then we can make sure that we're applying only a torque force here and not a lateral force. Okay, so when someone says that you should hold your torque wrench, perpendicular to this plate out here. Sorry, I'm not an artist. When they say you should apply this perpendicular force, if you're pushing on the torque wrench is trying to push this way, which means that we're applying a force this way, which is not adding to the torque on the nut. Makes sense? And if we're turning it anti-clockwise, we're trying to lean it this way, we're applying a torque this way, we're putting a tension in the plate. It's not adding any additional torque to the nut because it's doing exactly what we had on the previous page. It's just applying a horizontal load on the top of the nut. And the torque force is the only one that's where it's able to, tighten the nut. Okay, so does that make sense? That's where this confusion comes in. So if you're not using an extension, you have to be a bit careful. If you're using a decent extension, it's quite easy. Well, you have to hold the top because otherwise the whole thing will fall over. Okay, makes sense? Let's show that practically. Okay, so what I've set up here, just to prove that this works in the real world, is a scale, which is going to tell us how much load is being applied here. Here is our nut, right? So when we torque this nut, I think we can agree that I'm not adding. I'm like the first sketch, right? If I push this horizontally, I'm adding a force on this nut in this direction, and I'm adding a torque. Now that torque can be measured by our scale. 20 Newton meters is 2 kilograms. So if I apply 2 kilograms of torque, and this distance here is 500 millimeters, half a meter. So 2 kilograms, that would be 2 kilograms at a meter. So at half a meter, it's 4 kilograms of force we should see on this scale. And then when I move this to another location, so if I move it back to here, what I'm going to show is that it's still 4 kilograms. And if I move it all the way out to the end out here, it's still 4 kilograms. What I need to be careful of is that if I just push this, then the additional horizontal load that I'm applying here needs to be counteracted by this. So this would read more than 4 kilograms, right? It would be 4 kilograms from the torque plus an additional, whatever I'm applying up here, times this arm divided by this arm, right? So we're going to get a higher number on the scale. So anyway, let's move the camera and let's try it. Okay, hopefully that's an angle where you can read the scale. So I put it on this initial one. So this is our 2 kilonewton meters applied by half a meter, or divided by half a meter, should give us 4 kilograms. Can you read that? I think so. So if I apply, that is not going. Okay, you ready? 3.8. Let's see if I can twist it your way a little bit. Go again. 3.7 or so. 3.7 or so. Okay. So then if I move... okay. So that's with the handle in line. Oh, how am I going to show this? Okay, I don't know if you can see it from up there. I'm hoping I can get a good enough camera angle. Okay, so reset this. We apply our torque, 3.7 or so. Hopefully you can see that. 3.6. So if I'll move this down to the end now, to the furthest one, and I'll go at 90 degrees. Oh, how am I going to do this? Oh, there's the camera. Okay, 0 this. Okay. What was that? I can't see it. 3.4, 3.8, 4.1, 4. It's around that 4 mark. And then I'll turn this so that it's it's parallel. It should be the worst case. So it's still reading? No, it locks for some reason. Okay. What was that? 3.9, 3.8, close to 4, about 4. So is that in shot? Yeah. So basically, up here, we're at, let's measure this. So this is at 750 mil from the pivot. So what should be happening so it's 750 millimeters and then 500. millimeters. So whatever horizontal force we're applying here times 750 divided by 500, let's say we were applying a kilogram of horizontal load up here. 1 times 0.75 on 0.5 is 1. So for every 1, we should have 1.5. So we should be seeing a 50% increase when I had the torque wrench up here if the haters were right. But they're not. They're wrong. So I've shown it to you in diagrams, and I've shown it to you on the scale, and I've shown it to you on the computer. Okay? Settled? Thank you. Bye.